Everyone, my name is Arvind Niyampalli and I'm going to present my AI-based project titled as VoltAI, where we predict IR drop prediction using deep learning. So the main aim of my project is to predict IR drop in VLSI chip design using artificial intelligence. So IR drop is the voltage reduction that occurs inside a chip due to resistance and high current flow in the power delivery network. So if the IR drop becomes high, it can affect chip performance and reliability, and also which can affect the clock signal with the operations. So, traditionally, IO drop analysis is done using complex simulation tools, which are highly time consuming. So, in my project, I developed a deep learning model that predicts IO drop much faster using power distribution data. So, I will explain my project in detail, uh, including my all the codes, including my input files and output files, everything. Now let me walk you through the implementation part of my project. Here I have organized the complete project into multiple modules like dataset processing, model training, evaluation and visualization and front-end development. So first we will go for my dataset. This is my airdrop dataset, which are like .npi files. So I have collected this data from publicly available CircuitNet dataset, which is specially designed for VLSI physical design and airdrop analysis. So my dataset contains spatial and temporal power maps of VLSI chip layouts along with the corresponding airdrop information. So after collecting my data, I performed pre-processing and normalization to clean the data and make it suitable for deep learning training. So now let's move into my SRC folder. So this contains the core implementation. My SRC folder. These contains the core implementation files. So this is dataset.py file, which handles the dataset loading and pre-processing. And on my this is my model py. I implemented the deep learning architecture using 3D unit model with reusable connections and attention mechanisms. So the reason that I am using 3D unit is because the power consumption changes across both spaces as well as time. So the model can learn spatial and temporal features effectively. So next, this is my train.py file. The model training process is implemented where the network learns to predict IO drop maps from power features. And so this is my loss.py file, and this is my matrices.py file. Like I define performance calculations and error measurements to improve prediction accuracy. And also, these are my SRC folder files. So finally, I integrated the project with a web interface using Gradio, and currently the local web demo is running successfully on localhost. As I will show you. So this is my IR prediction dashboard. This interface is developed to make the prediction process simple and user-friendly for like VLS engineers and researchers, etc. Like here you can see that on left side we have navigation panel. So with different sections like upload section and predict and interactive demo and about model. And at the bottom the system status shows that the model server is online, which means the trained deep learning model is currently active and ready for prediction. So now comes to the main section. Here I have provided a section to upload 8.npi files. Like these are our input files. Like we will use 8 different power maps as an input, and we will predict the overall output IR drop by our my AI model. So I have already uploaded like for to save the time. So let's analyze the output. Here, once all the files are uploaded, the data is passed to the trained UD unit model. So the model processes both the spatial and temporal information and predicts the IR drop distribution across the chip layout within seconds. Like here you can see. So now this is the final prediction output generated by the AI model. So as you can see on the left side, we can see the input power map, which represents the power consumption distribution inside the VLSI chip. So here the brighter regions indicates high power activity, like where it has majority of switching activity. So while darker regions represents a lower activity areas. So the model takes this power information as input and analyzes the spatial and temporal behavior of the chip. So as you can see on the right side, we can see the predictor IR drop heat map generated by my learning model. So this heat map shows how voltage drop is distributed across different regions of the chip. So here you can see different colors. As you can see, blue, orange, yellow, and red colors are there. So the cooler colors like blue and green represents lower IR drop. As you can see here, like blue and greenish color, it represents lower power drop, which are comparatively safe and stable. Like warning colors like yellow, orange, and red represents higher IR drop regions. As you can see here, and it represents higher drop, which indicates possibly power integrity issues or critical hotspots. So as you can see in bottom, the system also highlighted something like critical hotspot detected, meaning the model has identified regions where voltage drop is significantly high and may affect chip performance or timing, reliability, etc. So, by using this visualization, VLSI designers can quickly identify problematic areas and optimize the chip design before manufacturing. So, this is my overall project demonstration, like how my AI model can predict airdrop patterns much faster than traditional simulations like LT Spice. So, which are my AI model will provide meaningful analysis for real world VLSI design. So, thank you.